All right. Hi, everyone. Welcome to the seminar. Today we have Ben Fish. Ben is currently an assistant professor in computer science and engineering at the University of Michigan. Before that, he held positions at Mila and the Fate Group at Microsoft Research. He got his PhD from the University of Illinois at Chicago as a member of the Mathematical Computer Science Group. And his research interests are in the foundations of fairness, justice, and other human values in machine learning and computational systems. And today he will tell us about the theory of discrimination in algorithms.
Hello, I'm Ben Fish, and I may or may not have way too much slides for the length of this talk. We will have to see. But in any case, the thing that I want to talk about today is that I think theorists have not yet created a satisfying theory for fairness or discrimination in algorithms. And so today I'm going to talk a little bit about why I think that, and about some threads that I think might help unstick us a little bit, specifically in relational quality and surrounding sociotechnical systems. Now, we know there are problems with their algorithms, and theory can be a very powerful tool for understanding those problems. We know those problems are about fairness and discrimination, but I think it's not always so clear what to do, especially as theorists, especially in large and complicated systems. There we go. So how do we know there are problems? Well, okay, many ways, but here are a few examples. This is a slide you have no doubt seen many times. And in each of these examples I have on this slide, we have some social system that is in some way mediated or shaped by algorithms. That's a sociotechnical system. And it's in part our algorithms that are causing these systems to fail so very badly. Now, guaranteeing accuracy and speed just don't appear to be sufficient to prevent these problems. Now, at this point, I think it's very clear that that's happening and these algorithms are somehow failing us. Of course, there are many different tools that we might apply here, like, just to name one, regulation. But what regulations or rules should we push for in the first place? Now, sometimes it might be obvious, but really I think it needs to depend on what's possible for algorithms to do or accomplish, not just in these particular instances, but in the future, in sociotechnical systems that have not yet even been built. In other words, this is a job I think a theorist can help with. So it's worth taking a look at what theory can do right now. Here's one, let's call it representative example of a computational or mathematical fairness definition. I'm sure many, if not most of you, have already seen this, so I'm going to skim through this pretty quickly. But what does this definition says? It says that a classifier is fair when two groups defined by some sensitive feature A get on average equal resources outputted by the classifier conditioned on members of those groups having equal qualifications, given by, in this case, the ground truth label Y. This is just one example of what I typically just call a group fairness definition. So here's a slightly more general definition of group fairness. A classifier F satisfies exact G1, G2 group fairness with respect to a sensitive feature A if some function of the confusion matrix, G1, is statistically independent from A, conditioned on some other function of the confusion matrix, G2. So for example, in equalized odds, G1 is just f of x, and G2 is just y. But the intuition about fairness here still holds. We want the resources to be independent of which group you're part of, given your qualifications. Now, this basic intuition about what fairness is holds not just for group fairness, but lot of, if not essentially all of the other definitions in the literature. So for just one example, a classifier F satisfies MM individual fairness if for every two individuals XY, we have the following property. Here, the groups are no longer actually groups, they're just individuals, that's in green, but the same basic property should hold. Now qualifications are determined by lowercase m. This property is saying if X and Y have similar qualifications in this lowercase m space, then they should also get similar resources determined by uppercase m. So the distance in uppercase m between f of x and f of y should be no more than the distance between x and y. So I'm going to sum up a huge amount of interesting literature by saying we can make this classifier under a broad array of circumstances. We can guarantee not only that any one of these definitions holds, or at least holds approximately, we can guarantee error rates, and to boot algorithmic efficiency as well. We can do so for not just classifiers, we can do so for MDPs, we can do so under social networks, and we can do so under all kinds of informational constraints, like, for example, missing values, especially when the missing value is the sensitive feature itself. So just to be clear, by sensitive feature, I mean something like gender or race. Now, of course, I'm simplifying here, but given that this is our current theory, the next question becomes, if this is our current theory, does it succeed as a theory? I think it's worth taking a step back and asking, well, in order to answer that question, what do we need out of our theory in the first place? And for that, let me give you a metaphor here. No matter how fancy a thing you build,
Can I interrupt you?
Oh,
Benjamin?
please.
But just like Omar has a point in the chat that says the metric is not always about qualifications. Yeah, and that's more like a like if
And just a quick comment that describing metric fairness as about qualification is not necessarily the right perspective on it.
So, of course, I'm simplifying here. It's not always the case that they are literal qualifications, though in some cases, it's absolutely the case that when these definitions are applied, they become a kind of qualification. As I'm going to talk about in a little bit, even when they're not qualifications, the intuition becomes that the definitions are used as a kind of moral dessert. Let me get back to this. If you still have more comments or concerns, let me know. But I'm going to address this a little more in a little bit. But I want to make sure that I have enough time. But yeah, so
your comments about this. I can read it if that's easier. Kevin,
yeah,
so
sorry, I don't have comments.
If the metric is not about qualifications, is it alternatively about like need or some kind of benefit or aligned with needs?
No, it's just about specifying the choice, the norms of society, which individuals should be treated similarly, rather than which individuals have similar qualifications. Perhaps society would decide at some scenario that people with similar qualifications should be treated similarly, but perhaps they would decide otherwise and incorporate other social norms.
Yeah, absolutely. The thing I actually want to stress here is essentially that point that this is not, of course, this is not value independent, and it's not just about equalizing resources without any additional constraints at all. It's about equalizing resources, or the output of a classifier under what we consider to be morally worthwhile. And often that's about kind of a literal qualification, but it can be about a more broad kind of norm or, moral qualification. Let me put a pin in this, though, just for the sake of time. To return to what I was saying about what we want out of a model. And by a model here, I really mean, just to be clear, the stuff that makes up, for example, the equalized odds definition, the groups, the resources, the qualifications, or moral qualifications. So in this metaphor, what I want to point out is that no matter how fancy the thing is that you build, it won't necessarily be enough. What we need is a model. In this metaphor, it's the model of the Turing machine. And the Turing machine is exactly so effective and powerful and creator of so much great theory, both because it's flexible and fruitful, capable of driving the theory. No model, no theory. So this is our model, right? This is the stuff that makes up what we get out of our theory. The classifier, the features, including a sensitive feature, the labels. It can also include other things I haven't talked about, like a utility function, even a utility function for every agent, or a causal diagram of features that helps determine which features are, causally important. But and this is, Omer, the point I think we were talking about. It also comes with an explicitly normative intuition, in this case for the objective function, that we're equalizing resources across people according to their moral desert, what they deserve, whether it be through literal qualifications or not. So given this model, there's probably lots of ways to split this up, but I'll talk briefly about three basic properties I want out of this. The first is that the model should somehow capture fundamental properties or trade-offs of some kind. In other words, a theory should be able to describe not what is right now, but what can be. I think that maybe the most famous result of this kind currently in this literature is that for virtually any two group fairness definitions you choose, they're not going to be simultaneously achievable unless you have some very narrow circumstances. So let's apply this result to an actual example. And the example I'm going to choose to discuss is kind of, if not the original one of the original ones. It's the ProPublica debate. I assume if you're in this talk, you've already seen this example a million times. But briefly, this ProPublica article was about the potential for racial bias in this classification system for risk, whether a defendant was likely to essentially commit another crime again. So, as the story goes, the company that produced this system ended up saying, look, I know you have concerns, but actually we're doing great. And we're doing great because we're satisfying a group fairness definition. A group fairness definition I haven't really talked about, but we're satisfying one. And sure, you think we're being racially biased, but it's only because you've chosen a different fairness definition. And these results say that these two definitions aren't simultaneously achievable anyway, and therefore, essentially, we're stuck. We have to choose one. And it's based on some kind of, maybe it's based on some kind of normative intuition, but we're just stuck with this kind of ethical debate, and there's nothing more we can really do. At least that's one approach to this problem. But here's another approach. Let's say that this classifier rates you as very risky because you're homeless. Now, the decision about what group fairness definition to make has nothing to say about this. But as the theory might go, being homeless, while does increase your literal risk, just because if you're homeless, you're likely to break laws that essentially only the homeless are likely to get charged with. But it doesn't mean you shouldn't get probation, that a high risk means instead you should go to jail. It just means that if you do get probation instead of jail, you'll need more help. You'll need help because you're homeless. This example, I intend to convey that somehow this debate about group fairness definitions, I don't think is making legible the normative consequences of these algorithms. That is, in this case, what to do if the defendant is homeless. There's something we're not capturing. And the thing that we're not capturing, at least one of the things, is the larger socio-technical system that provides both meaning and consequences to the state of homelessness. So on the one hand, it seems like we might be stuck. We have this debate and there's not so much it seems like we can do about it. On the other hand, you might say, well, that's fine because this is just not for, theoretical computer scientists to worry about. This is some social scientist problem. Let me just work on something I know more about. Of course, that's one tactic, but it's not the tactic that I'm willing to choose. And so when it comes to capturing fundamental properties as a theory, it doesn't seem like we're wholly succeeding. When we have this impossibility result, there seems like there's ways around it, right? And so on this, we haven't wholly succeeded, in my opinion. In other words, there's a way around this. Don't make sentencing decisions based on the defendant's life history. It won't work out for you. In fact, maybe you shouldn't be making sentencing decisions based on these risk scores at all. As I've said, there's something we're not capturing. Okay, so that's the first problem. The second problem is what I'm going to call emergent complexity. Basically, a theory should have more results than definitions. We now have a lot of these fairness definitions. I haven't even covered the half of them. But in exchange, what have we gotten? The resulting literature has largely been somewhere in the neighboring vicinity of constrained optimization. I put a pseudo-random selection of papers up on the slide. And I think it's a really interesting literature. I'm contributed a little bit myself. But I guess my basic hypothesis is that this literature won't last us forever. It's a great start, but I think we want more. At least I want more. So on this, while we've been successful so far, I just don't think the gravy train will last forever. And finally, maybe this one will be the most controversial for this audience. A theory should be able to guide practice. The most basic question we can ask here is, if we impose such and such constraint, does it actually prevent discrimination or injustice in practice? I claim the answer is kind of the answer is kind of self-evident. That's the word I want to use. It's self-evident. On the one hand, we have some version of disparate treatment, say being far away from group fairness. And this property, being far away from group fairness, might be a good source of smoke. In other words, there might be a problem here. There's often fire where there's smoke, but I don't think we should confuse the two. Blowing out the smoke, in other words, will not blow out the fire. Now, one possibility is that we have some easier way around this, like, oh, instead of group fairness, we should be using causal fairness. And I'll get back to this at the end, but I think essentially the moral intuition that is that the ethical theory that is baked into the definitions we have, including causal fairness, are not going to fix this underlying problem. And even if it does, which I don't think it does, these definitions in practice don't seem to be able to capture these kinds of most extreme examples of systemic discrimination, the very worst things that we might be the most interested in trying to prevent. And even if we can somehow make this work, these group fairness definitions, there's been already some debate over their legal justification. Who knows, in other words, what happens if one of these algorithms that uses group fairness goes up in front of a judge in Texas? Maybe not so clear. So on these three properties that I just mentioned, I think we're not wholly succeeding at any of them. But in thinking about these, we've already seen, I think, a couple of points at least that we can improve on. And in the rest of this talk, I'm going to talk about two. First, expanding the model to a broader socio-technical system. Just like in the ProPublica example, instead of just talking about the risk scores themselves, we might want to be talking about homelessness as well. That's not the example I'm going to use, just because that example is very difficult for me to think about. I'm going to use, I think, in some sense, a simpler example. The example is on content moderation. And the question we're going to ask. Another question?
Hi, so I wanted to ask, like, what practical, I think you might have mentioned here and there, but like what practical example should I think of where we are doing very bad in terms of like making any solutions for algorithmically? So you have this picture of like this, I think, I don't know, there was like migration or like people migrating from places. So like, is there some particular example where we are not doing well? Or like, should I think about the ProPublica debate as an example going forward?
So I skimmed over, I didn't even example I didn't even give explicitly any of these examples, but here's four. The top left isn't so much an example of migration as it is of genocide. This is an example of Facebook allegedly encouraging this genocide in Myanmar. And this is just one of many examples. That's a content moderation and recommendation example. We can also think about facial surveillance, encouraging, surveillance, even up to the extreme of
So beyond classification.
Yes, this is really beyond classification. This includes problems in representation, and I'll have a way of talking about, what the underlying thing that we want is. I haven't gotten there yet, okay. But I think the point is there's lots of problems of lots of different kinds, and it really is not so clear sometimes to what degree the algorithm is really meaningfully at fault, right? And so I have no easy answers for you here, but I'm certainly appealing on your intuition that there are problems based on what you've seen in the news and so forth.
Okay, yeah.
Does
Thank
that
you.
answer your question?
Yes, yes. Thank you.
So the next example is yet another example. So I'm going to give you yet another beyond the four at the beginning and the ProPublica example. And here I want to point out that in group fairness, you have to be told what the sensitive feature is. You're just handed it. Gender, race. There's, of course, the possibility that it's multiple sensitive features, but still, you have to be told what they are. In the case of, say, content moderation, where you're trying to produce a classifier that says whether or not a piece of content should be removed from a platform or not, you might have some ideas for what that sensitive feature might be. You might even try to encourage group fairness along the axes of many sensitive features, say exponentially many even, if they have low dimension, but still that's no guarantee that you'll hit the right one. The basic point here is that it's only by looking at the socio-technical system that we might be able to gain confidence that we know what the sensitive feature should be. So let me spoil at least one answer for you when it comes to content moderation. This is from a piece by, I forget, the Wall Street Journal maybe, which points out that Facebook's content reviewers working in the language of Arabic were all Moroccan. And there's many dialects in Arabic, like dozens. And just because you speak fluent Moroccan Arabic doesn't mean you can do content moderation in other dialects. And this holds true, most importantly for us, not just with the human moderators, but their algorithmic moderation as well. So here, in other words, the sensitive feature is not an exogenous variable. It arises from the particular history and dynamics of the socio-technical system. And it's only when we looked at this surrounding context do we know where this discrimination is likely to be. This is a dumb example, but if we're talking about assigning desks to students, whether they are left-handed or right-handed matters. That might be a sensitive attribute. But in content moderation, it shouldn't matter at all. Why? Because of the kind of system it is and the history of the system. So we should be able to, a priori at least, somehow have a way to understand this pattern from the system itself. So let me give you an example of a way to do this. Here's the more formal setting. A firm like Facebook collects or buys data to provide a product, in this case content moderation, in the form of a classifier to consumers. We're going to assume that the consumers all benefit from this increased accuracy. So this includes things like speech recognition or search, but not loans or insurance or what have you. And by benefit, I mean that the demand for the product is monotonic in accuracy. The more accurate it is, the less error there is, the more consumers will use this system. We're not going to fiddle too much with unfairness for now. We're just going to assume that what we should be looking at is a gap in error rates across groups. So how this is going to work, we have two populations, A and B, which we'll call the majority and minority groups. Crucially, I'm not telling you what the majority and minority groups are yet. We'll get back to that. But the firm is going to choose an amount of data to buy for each group, MA and MB. They're going to train their model as best they can. And they're going to come up with some error rates for each group. And finally, the consumer is going to react to those error rates by either using the system or not. So the first thing we need to do to understand how many consumers will use this product is to understand what the error rates will be as a function of the amount of data that they ingest. Well, there's a fantastic theory that tells us a very simple answer to this. We can use statistical learning theory here. So we draw a sample S from some underlying unknown distribution that's group dependent. We draw M sub G such examples, and then our firm is going to choose a hypothesis H from some class to minimize the empirical error. And then this theory, right, tells us that with high probability, the error on the underlying distribution is going to be no more than the minimum possible error plus some excess error, which depends on the amount of data that we've drawn, plus some other stuff that we don't, in this example, actually have to worry about so much. And this is agnostic pack learning, but in virtually any learning you can think of, your worst case learning bound will look exactly the same. That your excess error epsilon will be some constant. We're assuming here that the firm just fixes some probability of failure, divided by m to the 1 over q. In agnostic pack learning, q is 2, but this is essentially their learning rate. And as m goes up, epsilon goes down. To fully formalize this, now we need to understand how demand responds to these error rates. We're going to use linear demand, where the smaller epsilon g is, the more demand there is. Beta represents, in particular, the elasticity of this demand. Now, on the one hand, this is a very unrealistic assumption that consumers somehow respond to the upper bound on error rates. Most consumers, I find, are not learning theorists. But on the other hand, first of all, not even the firm knows the true error, so we can't use that. And really, this just means that consumers are responding proportionally to m to the 1 over q for some q, which should be the case anyway if they had responded instead to the empirical error rate, at least on average. Data is also costly. We'll assume that the cost is linear in the size of the data. And now, with this in mind, we can write down the profit for the firm. The firm is going to maximize their profit by choosing the amount of data points m such that revenue minus cost is maximized, where their cost is given by the cost of buying the data, and the revenue for each group is multiplying the demand by the size of the market, the amount of people in that group. The tricky part here is that more data means more revenue, but also higher costs. So the goal here is to find an equilibrium. How much data do they actually buy? I'm going to skip proof, which is very easy for the sake of time. I get right to the theorem, which is that at any optimum, for any pair of groups, the error inequality is this. So we have the minority group on top, the majority group on the bottom, and the error inequality is going to be the product of the ratios of their relative market sizes, their relative elasticity of demand, and their relative costs, including both learning costs and data costs, all multiplied to the 1 over q plus 1. This tells us what the minority group is in the first place, at least when it comes to their incentives created by buying data. The minority group has a higher cost of data, is smaller, and is less elastic in their demand. This gives us an answer for why potentially Facebook's enforcement algorithms weren't capable of handling these different dialects. It gives us a way to say that we can, at least in this particular example, have one way of figuring out what's likely to go wrong in the first place, where this sensitive feature is likely to lie. It's likely to lie in groups where this firm has to buy separate data and has these properties. So this is just a very simple example, but I'm already low on time, so I'm just going to move on to the second thing I want to talk about, which is an alternative ethical theory for this model. And to understand what I mean, let me use yet another example. We're going to use a very simple bargaining model of a hiring market. There are multiple reasons to consider hiring markets in the first place, but at the very least, they've been, since the time of Arrow and those guys, been a place to better understand discrimination. Now, this particular model is going to be essentially as simple as possible. There's going to be two players, the firm and the candidate. The firm is going to offer a split of a unit surplus, which is the total benefit the firm and the candidate get by entering into an agreement. The offer may depend on the candidate, so we represent this offer as a classifier F. If the candidate accepts this offer, well, then they split the surplus as the firm offered, the candidate getting F of X and the firm getting the rest. On the other hand, if the candidate rejects, essentially for the sake of simplicity and well, for technical reasons I won't tell you, we're going to represent the entire rest of this market as a single player called the open market. And the open market won't act strategically. They're just going to hand them, both the firm and the candidate, their outside options, which here I'm calling OX and OF. As before, we're going to look at the equilibrium in this game. Well, here's one. The firm will offer none of the surplus to the candidate and keep everything. The candidate believes, it doesn't even have to be true, just that they believe that if they reject this offer, they will receive 0 from the market. Their outside option is no better. So the candidate is indifferent and accepts this offer and never sees what they would have gotten if they had rejected instead. This is called a self-confirming equilibrium. I won't formally define it because the intuition is way more simple than the formal definition, which is very confusing. But the intuition is one where the beliefs of each player only need to be correct on the equilibrium path. So this is one self-confirming equilibrium. Let's look at another. This is going to be very similar to the first equilibrium. Now the firm offers half of the surplus instead. And the candidate believes it still doesn't have to be true, just they happen to believe that if they reject and say interview elsewhere, go on the open market, they will receive that same utility of 1/2. Again, the candidate's indifferent between the two options, and so accepts this now much higher offer of 1/2. Here's the thing. Both equilibria are outcomes, even though neither depended on the true outside options. Everyone could have been wrong here, both the firm and the candidate. And they could have been wrong because they never observed the open market at all. It also didn't depend on any features of the candidate. All possible candidates, we can assume, are equally qualified for this position. Yet, a candidate stuck at this first equilibrium, equilibrium A, where they get nothing, despite a much better outcome existing, has no rational way to escape since it's at an equilibrium. A candidate, in other words, is trapped with getting nothing for no good reason that I could possibly come up with. And for that reason, to me, it appears blatantly unfair. So now let's go back to the definitions we have and see if it prevents this from happening. What are the definitions we have? They say we should equalize resources, here the amount of surplus they're getting, across people, the candidates, according to their moral desert. This, it turns out, is a form of what we refer to as distributional equality. The point of equality is to equalize stuff, resources, or access to resources across people. And this distributional equality, it will turn out, will not prevent this unfair equilibrium. Simply put, two different candidates, X and X prime, could get wildly different amount of resources, but all candidates are equally qualified. I'm going to suggest, so I should say, I'll get back to in hopefully very soon, a more formal version of the statement, but for now, I'm going to suggest an alternative ethical theory. We need to suggest an alternative ethical theory just because none of these distributional equality-based notions are going to prevent this from happening. The ethical theory I'm going to use is called relational equality. Particularly, I'm going to focus on the variant from the political philosopher Elizabeth Anderson. Her relational equality is very different than distributional equality. It says that the goal of equality, the proper positive aim, is not to ensure that everyone gets what they morally deserve. This is what we just saw. But rather to create a community in which people stand in relations of equality to others. What does this mean? This is really where the rubber meets the road, because if an ethical theory is to be useful for, well, theorists, we need something mathematically tractable. Anderson goes on to say that relational equality regards two people as equal when each accepts the obligation to justify their actions by principles acceptable to the other. This is a confusing sentence, I think, but in our very simple case, the only possible outcome is utility, and the only goal is to maximize utility. So the only possible principle that could be acceptable is to maximize the other agent's utility. In a constant sum game, this can't always be done. But at the very least, we can make sure everyone gets positive utility. Where there are two equilibria in mind, we can now define the following. We'll call an equilibrium to be blatantly unfair to a player X in a two-player game. I'm going to assume it's complete information. If one, the payoff for X isn't positive, which happened in our first equilibrium. But two, there is an equilibrium, that was our equilibrium B, where both players receive positive payoffs. They have attempted at least to justify their actions by principles maximizing utility acceptable to the other. Now, finally, we can go back and formalize what I've already said, which is there exists a classifier which can be played by the firm that is at a blatantly unfair equilibrium. We think it's not fair, and we think it's not fair because it doesn't satisfy our conception of this Andersonian relational equality. Yet, this same classifier satisfies group fairness, like equalized odds. It also satisfies individual fairness. It satisfies your favorite causal fairness definition, and it even is not an example of some economic forms of discrimination, like taste-based or statistical discrimination. This is an impossibility result that says you can't be both group fair, for example, and non-blatantly relationally unfair. But if you agree with me that this very simplified example captures some real kind of discrimination, say by justifying according to this theory of relational equality, then this result is stronger, right? It says that these computational definitions of fairness, in the worst case, fail. Particular, it also says how these traditional economic explanations of discrimination are at the very least incomplete. So for example, in so-called statistical discrimination, candidates who aren't hired are less skilled at equilibrium, which in turn, according to the firms, justifies them not hiring them. And because they're not hiring them, there's no reason to invest in skills in the first place. That's statistical discrimination. Here, though, even at equilibrium, all candidates are equally skilled. And yet this form of discrimination still can happen. So this means, at least to me, that existing computational economic definitions of fairness are likely doomed. Let me be, blunt here. They're doomed to fail because of the ethical theory that underlies them. Their basis is distributional equality. Moreover, they largely only depend on the output of the algorithm and not the surrounding socio-technical system. And even worse, I think we can only go so far if the only visible outcome, as it was in this simple game, is utility. We will always end up with some welfare function, just as we did here. But relational equality is not just about utility. It's about somehow the relationships that bind us together. I think overcoming the challenges I've outlined in this talk will be both very difficult and the defining crucible that will decide whether or not theory can be successful at tackling these ethical and normative criteria. I don't know how to do this, but I'd love to hear your thoughts. Let me thank my wonderful co-authors on the work that I've mentioned here, and thanks for listening.
Thanks for the talk. Are there any questions for Ben?
So I have a question. Yeah, thanks for the great talk. I had a question in the first paper you showed. So there, if Facebook has this constraint that it needs to be have equal error rates for different dialects, isn't that better? Like that's like a group fairness constraint that can help this situation.
Yes, so in this example, it's not that group fairness is, oops, I don't know what just happened. It's not that group fairness is bad here. It's not like we should be avoiding it. It's just that it's hard to know how to apply it. It's hard for me to talk and find the right slide at the same time. I went way too far, didn't I?
Yeah, I think you went too back. Yeah, this.
It's hard to know how to apply it. That is, choose a sensitive feature or features without looking at the larger system surrounding this content moderation classifier. Yeah, it would be great if we could get group fairness across every single dialect of every single language. It would also be great if we could get group fairness according to, say, the particular kind of slang they use, or their gender or race, or I don't know, some other things that I haven't thought of yet because I'm not an expert in content moderation or NLP.
Mm-hmm.
But at the very least, I wouldn't have even thought of the problem of dialects in Arabic without looking at the incentives that Facebook has. So it's not that like we don't want group fairness in this case. We might want it or we might not. That's always going to be at least part normative question. But the theory that we have, someone else hands us a sensitive feature and we do constrained optimization, doesn't totally tackle the problem because it doesn't tell us at the very least what the sensitive feature should be in the first place.
Okay.
Is that a partial answer?
Yeah, this sounds good. Thank you.
Right.
I have a few comments, perhaps. One is that this notion of not knowing the sensitive feature has been the focus of a lot of work in the last 5 years or more. And there's lots of work on actually not trying to identify the sensitive feature, but addressing a large collection of groups. Another comment I want to make is that I don't know if this, there's an all or nothing kind of sentiment sometimes that either you solve everything or you're doomed, which I don't know how reasonable it is. And the third thing is that perhaps a lot of what you've been talking about is very consistent with the work on composition. And there have been various approaches in that respect. And this is kind of mirrors a lot of what happened in cryptography, where there have been lots of standalone notions. And it was a challenge for the community that took a lot of time to address compositions. There have been some very interesting work on compositions with some solutions to very similar scenarios as the one you're describing. But I think that it's a good additional step in what is a very reasonable and natural progression of the theory, rather than a paradigm shift, in my opinion.
Yes, okay, lots of things to address there. So I certainly apologize. I'm certainly aware of the literatures that you pointed out. I tried to squeeze a lot in, so I didn't have time to talk about them in any detail. On the subject of, where should I start? On the subject of many sensitive attributes, I think that's the first thing you mentioned. Yeah, I really like that literature. I think it's great. But as I mentioned, there's really two problems here, I think. The first is that even if you do successfully manage some approximate group fairness for exponentially many, which there's been several papers on, there's still no guarantee that you've hit the right one for the particular problem at hand. And the only way we'll know what that sensitive feature is to look at the actual sociotechnical system. It has to come, I think, from, sympathetically from the history, from what people are actually, worried about. And specifically from, I'm not the first person to point this out, I should mention, what's her name? Anna Lauren Hoffman has some good work on this, but when it comes to systemic discrimination, it's about the creation and maintenance of these social categories as categories themselves, and that's done through the the dynamics and the structure of the system. And so that work, while certainly, I think, a real interesting improvement over single sensitive attributes, doesn't address either of those issues. On the subject of composition, yeah, I mean, I've heard of this. I've heard this metaphor being applied, especially when it comes to differential privacy, right? So, like, differential privacy is a real step up over previous standalone definitions of privacy, in part exactly because of this composition property, right? And I agree, it's a great property to have, and I thought that the papers trying to move this property into kind of the fairness work are very interesting. But again, I don't think it solves some of the underlying issues, which is, if you're going to make sure that some property composes over multiple mechanisms, it's still important to understand what that property actually is. What are we ensuring? This is where I'm trying to head at the end of my talk, right? So if we somehow manage to make distributional equality compose, that still doesn't solve the underlying issues of the ethical theory that we're basing our constraints off of. I should say I was being maximalist in my talk in terms of provocation. I was being as provocative as possible. I don't mean to imply some binary where either you solve everything or you're stuck with what we've got. But ultimately, I'm not sure I agree with you that the only, say a piecemeal approach where we make no major changes to this kind of underlying model and theory I've been talking about will be sufficient. I think it will take major changes. And that's not to say that our existing work is bad or shouldn't have been written in the first place. And if it is, then I'm as much to blame as anyone, because I've written it just the same as everyone else. But that doesn't mean I don't think we should push for more. I think those are some of my responses to some of your comments. I don't think I hit everything, but I've forgotten what else you said at this point. I'd certainly be happy to talk more offline or online. I am aware I made this talk a little bit provocative, so I hope you don't mind too much.
Do we have more questions for Ben?
Can I ask one question on the more technical side of things? So
Please.
you showed us a extensive form game, and I didn't quite understand the outside options that you had there. In particular, like I don't really understand what type of equilibrium notion you were considering to prove your point here on this slide. So yeah, like what is the equilibrium concept? I mean, over here, I mean, if the outside option is better, people, would take it. So what exactly are you thinking about? It's not like equilibrium you described, it's not like, let's say a subgame perfect Nash, or like even a Nash for this.
No, this is not a Nash equilibrium.
Yeah.
The equilibrium concept is as I briefly mentioned, I really skimmed over this, a self-confirming equilibrium. The idea here is that under a Nash equilibrium, you have to be correct about what people will do on all paths. So for example, you know what the market conditions are. You're going to get such and such salary. And and because of that, if the firm ever offers anything you below market rates, you'll immediately go to the market. But well, a couple things. One is the kind of, that's not always the case. There's many hiring markets in which salaries are somehow hidden. The simplest case is kind of the case where, think like fast food. McDonald's just posts their rate, which is probably somewhere in the neighboring vicinity of minimum wage. Everyone knows that's what you're going to get. And there you're much more likely to end up at some kind of Nash equilibrium. But in many hiring markets, like for example, things that are seen as having higher, skill requirements, like the academic market, there's much more uncertainty. And so both the firm and the candidate might not know what will happen if they break apart, that is, the candidate doesn't accept in this model. And so the idea here in a self-confirming equilibrium is that if players play this game repeatedly and only learn about their opponent's strategies, if they actually go down that path, then what will result will not just be a Nash equilibrium. What will result will end up being a so-called self-confirming equilibrium, where the players will only be correct about what their opponents will play on the equilibrium path, on the paths where they actually travel, and not on the paths where they don't travel, which in this case is the open market path. Does that give you, I haven't formally defined it. In fact, I didn't even, the definition of a self-confirming equilibrium requires some staring at, so I didn't include it, just because the math looks worse than it actually is. I think I didn't even remember.
Yeah, I understand. Yeah, I understand what you mean. Yeah.
Great. So I should have remembered to put an extra slide on that, but I forgot.
All right, I guess we are slightly over time, so we can end the seminar.